Okay guys, good morning. Ready to go? Aromaticity warm-up here. Some warm-up questions. Aromatic rings, yes or no? Types of questions. Over here. We know the benzene ring, yeah? Benzene ring. We'll be looking at other aromatic rings. Thiophene ring, is it aromatic? Piperidine ring, is it aromatic? Just because it's a ring doesn't mean it's aromatic. Okay, so we have to understand what an aromatic ring is. Aromaticity. And so we have, but you know the traditional benzene ring, we've always called that aromatic, right? These rings that contain a heteroatom, hetero meaning non-carbon, different from carbon, these are called heterocycles, heterocyclic. Okay? And heterocyclic chemistry is very diverse and very common, and all these drugs contain heterocyclic rings. Okay? Benzene is not heterocyclic, it's just carbocyclic, are all carbons. But over here we have a pyridine ring. The ring has one nitrogen, it's a heterocyclic. Okay? So, lots of common drugs with lots of common heterocyclic rings. Some of them aromatic, some of them not. Intro to benzene and aromaticity. Okay, the other handout is sort of our outline. And it looks like we're beginning with structure of benzene. Okay? And we will get to that. All right, so two different outlines here. Let's begin with this here, though, the white page intro. Okay, benzene. Formula C6H6. Okay. 4 degrees of unsaturation. You see that from both structure and formula. Okay. Benzene is a liquid with boiling point at 80 degrees Celsius. Water being 100. Okay, so it boils at a lower temperature than water. It's a pretty good solvent. Okay. It's pretty non-polar, but the pi electrons are very polarizable. It helps it become a good solvent. Problem is, it's got a nasty habit of causing cancer. It's a carcinogen. And while it used to be used a lot 100 years ago, 50 years ago, these days it's not used as much as a solvent because of toxicity. Today we use toluene, still use toluene. Toluene is what? Okay, well, we'll have to learn nomenclature of aromatics. That is by video only, and it's posted on the YouTube page, and I will send you, or is it in one of these handouts? Is nomenclature in here? It might be a separate handout. Yeah, it is in here. It's on the back page. Okay, so you already have the that. We can take a look, quick look back there on the back page, and there's some common aromatics you need to learn. And toluene is what? Benzene with a methyl. Okay. We used toluene organic one when we did a Diels-Alder reaction. I think we did. Toluene is much safer. It's not a carcinogen. Just adding the methyl. Why? Adding the methyl. Toluene you can buy at Lowe's in the paint section. You can't buy benzene. Okay, it's more restricted. Okay, benzene was first isolated in the 1825, somewhere in there, from well fat. Well fat used to be burned in the streets in street lamps as a source of fuel. And working with it, they would observe that this vapor, this residue, could be kind of collected and distilled out of this well fat, and it ended up being benzene. Now, when somebody first got, who was that somebody? Well, it actually was Michael Faraday, famous for being a physicist. But he's the one that actually isolated benzene from well fat. He actually did a lot of chemistry. And there's some of his notebooks have survived, and there's some of his writings. He talks about distilling this compound and trying to get a pure fraction, and it's very fascinating. Now, when he got this liquid, he didn't know the structure. They didn't know carbon-carbon double bonds existed until like 1860s. Had no idea what structure was, but they knew it was a liquid that wasn't water, and it had certain properties. It had a boiling point of 80, not 100. You know. Now, the structure actually wasn't determined until 50, 60 years later. Okay. Before the structure of benzene, this, which seems so simple, and okay, but when you have no clue, you know, how do you know this is 6 carbons in a ring with 3 double bonds? I mean, you're just looking at a liquid, right? Well, there were many other structures. They could do, back then, 200 years ago, they could do elemental composition. And they could thus do empirical formulas. Pretty close, you get that. And so they could tell it only contained carbon and hydrogen. And they could tell the ratio of the two. Okay? And so the first thing they figured out was it had that empirical formula. Or a multiple of that, but an empirical formula. And many structures were originally proposed. This is one of the original. It's now called prismane. And I think that structure is now known, but they thought that was originally what this thing was they got from well fat. And you see it has the same formula. It has 4 degrees of unsaturation. Because there's actually 4 rings there. There's no double bonds, but it's just 4 rings. It's a very peculiar looking arrangement of atoms. But that was one of the many structures that was first proposed for benzene. Until someone by the name of Kekulé actually came up with this structure, and eventually it was proven that that's the structure. How was it proven? Well, we could keep talking and talking. But that's some of the story. Kekulé, by the way, is the same person who sort of confirmed the structure of acetone, which is what you wash your glassware with. Okay. Okay, the structure of benzene. All the carbons are sp2, right? Every carbon is trigonal planar with 120-degree bond angles around each carbon. All right, standard trigonal planar, sp2. You should recognize that. We can show the sigma framework, just the sigma bonds, and it's the sigma bonds are in the 120-degree bond angle. Trigonal planar, 120 degrees. Okay. 3 bonds to this carbon all flat on the board, none forward, none back. Okay. Planar. Then with an sp2 carbon, each remaining carbon has a p orbital, right? And we can show the p orbitals. Okay, so this would be just the sigma bonds, and this we can call just the pi framework, or the pi network, just showing the p orbitals on each carbon. And each one has 1 electron. Okay, and if we show them, they're all interacting. They're all overlapping with each other. And back in Organic 1, when we looked at functional groups, I gave you a beginning definition of aromaticity, and it was what? An aromatic compound. On the functional group handout from Organic 1, you got it, right? I know you guys don't have my handout, but other guys do. And what was the definition of an aromatic compound? All what? Close. First of all, it doesn't have to be carbon. We can broaden it out. All the atoms have, perhaps, but it was stated another way. All atoms have a p orbital. Yeah. Which kind of requires sp2, but I have to think, does that always apply? What does apply is every atom has a p orbital, and they're all interacting. And there we go. Every carbon has a p orbital. They're all interacting. Okay. And so it's 6 pi electrons because each one has 1. Okay. And all this right here you should all know, but I guarantee you that you need to review all that, because if we discuss this with some other molecule out of context, can you get all those same answers real quick? Do you really understand structure and bonding going on here? ultimately, we typically like to draw localized double bonds. So is the double bond, what is a pi bond? P orbital with one electron, P orbital with one electron interacting to make magical pi bond? Okay, well, there, and there. What if those three, what if these two are interacting, those two are interacting, those two are interacting? We would draw 3 pi bonds and it would look like what? Like that? Well, why do it like that? Why instead of these two interacting, why not show those two interacting, those two interacting, and those two interacting, and draw it like that?
All the same.
Well, which one's right?
Both.
They're both. Okay? Because ultimately, what do you have here? It's ultimately a continuous overlap all the way around, what we call resonance or conjugation. And with resonance and conjugation, it's very hard to show a discrete structure. The true structure is actually a hybrid, a blend. But just showing blends all the time can drive us crazy. That's why we like to draw fake structures instead. That's what we do as organic chemists. So these two are fake, true structure, okay? If you wanted to draw resonance, you could just pull these down, windshield wiper these over, and windshield wiper these up. What does all that arrow movement give? Well, it should give that over there if you want to just go from one resonance structure to another. So we have good delocalized bonding, 6 pi electrons over 6 p orbitals. Now some people will draw benzene actually like this, or actually people will draw benzene, just do that, okay? Because it's a continuous overload, okay? Which is really they're trying to show this. That is, back over here. What's the bond order between these two carbons here? Is it 2 or is it 1? 1.5. Which resonance structure is major? They're equal contributors, so it's going to be a perfect blend of 2 and 1, 1.5. Okay, and if you look at it, it's 1.5 all the way around. So it's like a bond and a half, a bond and a half, a bond and a half. And so that's what you end up with. And if you draw that sort of circular, you kind of do that. And if you go, and if instead of doing da 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 da, you just do this, it's kind of, that's how you get to that point. I'd recommend never drawing benzene like that, though. Never. Sometimes it's okay. And never do this with a heteroatom. Once you have a nitrogen or a sulfur in the ring, never do that, please. Because it's just too simplistic. And the next problem is, how are you going to do a mechanism with this? We ain't going to be able to do it. Okay? To do a mechanism, we need to use one of the fake structures. All right? Because that's more the traditional moving the electrons. How do you move a circle of electrons? Okay? So you got real life, but we have sort of our what we practical do stuff. All right? All right, what is the evidence for delocalization? And we're eventually going to get to the green sheet where it's kind of outlined there. All right? And A, is that A there? Mm-hmm. Bond order and bond lengths? Okay, kind of like that. First, evidence for aromaticity. How do we know it's aromatic? What does aromatic mean? And how do we know it's aromatic? Well, the first thing is all carbon-carbon bonds have the same length. That's not just theory. We know that. If you look at benzene, every carbon-carbon bond has the same length. Now, if it was this structure, the bonds would not have the same length because we know that a single bond is longer than a double bond. So if it was single, double, single, double, single, double, benzene would not be a perfect hexagon. It would be long, short, long, short, long, short, and it would look all kind of skewed, like uneven bonds. Because if you look at an alkane, that carbon-carbon bond is longer than an alkene carbon-carbon double bond. But we know benzene is a perfect hexagon with every bond length being what? Sort of just between the two. Now these are probably rounded off, and that's probably rounded off, but this is kind of right between the length of those two. Which kind of bond length kind of comes from bond order. What did we say the bond order was between each carbon? 1.5. So it's in between these lengths. Okay? How do we know what it looks like? Ultimately, X-ray crystallography. That's traditionally the closest way we've ever come to seeing molecules. Today we can do some type of microscope that are becoming so powerful you can almost see molecules. But 50, 80 years ago when X-ray crystallography was invented, it really allowed us to see molecules, to see the molecules. And if you look on the next page, I think from where we're at. Now benzene is a liquid. And it's hard to get a crystal structure of a liquid because you need a crystal. And maybe it can be done at cold temperature when benzene freezes and then you get it maybe. Okay. But we have plenty of crystal structures of solids. This is a compound that was made in my research lab a while back. And it has two benzene rings and then this heterocyclic ring. And this is an X-ray crystal structure which was obtained in Emory. We send them crystals and they send back this data. And they send back a structure. And this structure here comes from data. Okay? And the data, lots of data supplied, but it supplies bond lengths, bond angles, stuff like that. Can be obtained from X-ray scattering, and this can be turned into a structure. Very powerful, lots of math, higher level math. What type of bond angles did we see around each carbon? 120? Okay, well you see 119. Now again, things can deviate. 109.5, is everything always is tetrahedral always 109.5? No, we learned you can deviate from that. Okay. So it's pretty darn close. You see all these are pretty darn close to 120. Okay. This is also experimental, and so there's possible some error. 120 is kind of our theoretical standard. Okay, but when you do experiments, there's a little bit of error built in. Okay, so a combination of error, but also knowing that 120 is just sort of a very theoretical. And you see in the structure, can you see it's kind of 3D? This ring looks a little flat. But can you tell that this benzene ring over here is a little bit sort of turned like this? Can you see the 3D nature? Now this is printed on the page. You can also get this, you have a computer program to allow you to see this 3D, and then you can start turning it. And maybe when you start turning it, you can see if one ring's flat, the other one's more like this. Maybe if you turn it, you can see that. Okay. But that is also a result of the X-ray. And you can see how the compound exists in the crystal structure. Okay? With all these bond angles, again, maybe in the crystal structure it's like this. The two rings are like that. You know, and then they repeat to make crystal, crystal, crystal. Okay? Now, that's different from how it may exist in solution. This isn't a crystal structure. When it's in the crystal, everything is sort of arranged very uniquely. But when you dissolve it and things separate, then the conformations can change. Okay, so ultimately this data can come from X-ray crystal structures. Very, there's lots of people out there who that's all they do. They're X-ray crystallographers. And they spend their whole career working with that type of instruments, and very powerful. DNA, how was DNA the structure of DNA confirmed? Well, many different ways, but one way there was some X-ray crystallography. And I think there was a lady back then, was it Dorothy something? Was Rosalind Franklin? Okay. And did she do crystal structure? Okay. Kind of competed with Watson and Crick over that. But crystal structure was big. And throughout history, in the organic chemistry history, getting a crystal structure often kind of proved structure. help advance things. Because you can get NMR, you can get IR, but crystal structure can be very powerful. Okay. Now, this Kekulé, back in the 1860s again, when he wasn't working with acetone or other stuff, he got interested in aromatic compounds, and this compound that Faraday had isolated, 20, 30 years earlier from well fat, and then they started doing chemistry. I don't know what this liquid is. I know it smells peculiar and the boiling point is 80 degrees. That doesn't mean I can't do reactions on it. Maybe I can react it with bromine. I don't need to know what this is to react this with bromine. But then I get another product and I'm like, wow, I got a product that ain't this. My product contains bromine now because I can determine elementals. I don't know what either are, but I know they're different. Wow, then I'll do reactions on this. And but before long, you've made 10 different compounds. You don't know what they are, but you know they're all different, and you know they're all pure, but you're still like, well, then 40 years later, people like Kekulé, in the 1860s, Kekulé actually tried to isolate these two different compounds. He's like, I think this is the structure, and we should have two here. But guess what? He never could. He ended up just wasting his time. Because those are actually the same compound. Okay? Right? Because if you instead just draw the rings like this, you see that those are really just the same compound. So, he spent a lot of time and just didn't have any success. I think he just gave up because the structure is that there. Yes?
Why did he think that they were two different structures?
When what?
Why did he think that they were both two different compounds?
Because this one, the double bond is between the two bromines, and this one, the double bond is not.
Okay.
And so drawing these out on this paper, parchment paper, whatever they used back then, he's like, the double bond should be between the bromines, and then the double bond should not be. I think this should be two different compounds. I'm going to try to isolate them and prove this. And he never could. Okay, we cover everything there. Reactivity. Before we look at activity, let's give let's advance our definition of aromaticity. Every atom has a p orbital in the ring, right? I gave you that week 1 of organic 1. So back then we were learning to identify p orbitals, and okay, that was okay. Now new definition. It's an unusual stability as a result of full cyclic conjugation. Now full cyclic conjugation is every atom having a p orbital. Okay. But this leads to an unusual stability. What are we talking about? Well, let me give you some evidence. If you take benzene and react it with bromine, we know that pi bonds react with bromine, you get a trans addition. You did this reaction in lab, my guys did. Did you guys brominate trans-steel-beam? Typical reaction around here? Okay. Trans addition, well guess what? That's an additional reaction. Benzene doesn't do that. And in organic 1 I said we never do any of this chemistry, alkene chemistry with benzene. Not in this class. Wait till organic 2. Okay. Benzene doesn't react like a regular alkene. It's not a compound with 3 alkenes. It doesn't do that. Instead, you react with bromine. First off, it's a little sluggish. Alkenes react with bromine almost instantaneously. You remember adding bromine, hand behind your back, and it reacts very quickly, color goes away? Yeah. Benzene won't react that quick. Typically, you have to add in a catalyst to get it to react at a decent rate. Okay? And instead of getting an addition reaction, you get substitution. An H is replaced by bromine, and the other bromine joins up with that H, and you make HBr. Up here, you don't make HBr. That's just a simple addition. Okay? So, the key thing is that something must be, it's trying to maintain this 3 pi bond thing. It's maintaining the aromaticity. It must be good then. We did this, You would lose the aromaticity because these two carbons are now sp3 and they do not have p orbitals. The aromaticity is maintained. But this is unusual reactivity for pi bonds. Substitution instead of addition. And indeed, benzene compounds do substitution instead, so the benzene ring is maintained. Other cases, if we have an alkene, can't you cleave an alkene or do a, well, this is actually a cis diol. Won't these react with alkenes to give cis diols? Yeah? Chemistry? Well, guess what? These will not react at all with benzene. No reaction at all. So again, there's something unusual about benzene. All right? Less reactive, and it seems to be unwilling to destroy the magical 3 pi bonds there. So that implies that the 3 pi bond type setup is something good. Okay. Next thing is heats of hydrogenation. Remember this in organic 1? You hydrogenate an alkene to an alkane, H2, some type of catalyst, palladium, nickel, platinum, etc. Okay, just an addition of H2 is a syn addition. We had stereochemistry. Okay, this is a reduction because we're adding H's. So if you reduce the alkene to the alkane, it's exothermic. Because we're going from a pi bond to 2 new sigma bonds. Remember all this? Same discussion for organic 1. Exothermic. If you have a diene in the ring, okay, like a double hydrogenation, but you don't get double the heat. Double that is what? 236? Instead of 236, you only get 230. Why do you get less than double? Is this simply 2 double bonds? What's after this? Benzene? Look at the difference here. If you do this one, this one's going to be more like, what's double that? 236? 236 kcal, kilojoule. I usually do kcal. This is kilojoule per mole. 118 times 2 would be 240 minus 4, 236. Okay. Why would this be 236, but this one only 230? First off, what is the difference? What does the numbers imply? Which one is more stable? 236 or 230?
236.
This one's more stable. It gives off less energy. Why is that more stable than this? Because it's conjugated. Conjugated diene versus non-conjugated. Conjugation makes it more stable. If it's more stable, it has less energy to give off. So that makes sense? Okay. The more stable a compound is, the lower energy it has. And thus, if you hydrogenate it here. Now, if you go to benzene, the heat of hydrogenation is actually 205. Now, that's not triple. Triple of that would be what? It would be 300 and something. Like 334. Okay, I'll take your word for it. Something up there. Why is this so much? What does the number imply? It's much more stable than just a triene. This is not just three double bonds. It's not just 3 of those. It's much more stable than that. It's actually more stable than this. Why? Because putting 3 in there, it is now what? It's now fully conjugated aromatic, and that's very special. Very low energy, relatively. Okay? It's not just 3 double bonds. Also, if you try to hydrogenate benzene, the traditional palladium platinum just don't work that well. You need a stronger catalyst, something like rhodium. Okay, it requires a stronger catalyst to do it. Yes.
So with the 3 bonds, how is it, like I'm assuming with the 1 bond, the double bond's attacking one of the H's and then the other H is going to the carbocation?
No, hydrogenation is not a carbocation. It is a catalyst for 2 H's, 2 darks. There's no intermediate.
So with the 3 bonds, would that mean that there's multiple?
It would have to happen 3 times,
Okay.
yes. Yes. I mean, if you hydrogenate, one double bond will be hydrogenated first, and then the next, yeah. I mean, there is potentially an intermediate here. Yeah. Yeah, and I'm not balancing this. This is going to require 3 equivalents. This is going to require 2 equivalents of hydrogen. Yeah. But if you look at the handout from Organic 1, where we looked at alkene hydrogenation, okay, syn addition, okay, the 2 H's come from the same side. We didn't look at the mechanism because it's not well defined. There's no intermediate. It's just a transition state. All this was in Organic 1. All right, no carbocation. Look back at that if you want to know that. Okay, so heats of hydrogenation can tell us, is the compound just a triene? Okay, is this just a triene? Or is it aromatic? All right. Is it just 3 alkenes in a ring? Or is it something more than that? Indeed it is. And the heats of hydrogenation can sort of give us some data to tell us, hey, something unusual here. You know. By the way, the difference, it looks like 118 is 354. See, I knew I shouldn't trust you. That seemed too low. 354 minus 205, we got 149 not accounted for. It ain't just a triene. If it was just 3 double bonds, it should be 3 times whatever 1 was. It's much less. The difference is 149, that's kind of called aromatic stability. That's the amount of aromatic stability. It comes from the magic of the conjugation. NMR. Aromatic H's are where in the H NMR? About 7 to 8 ppm. An alkene, about 5 to 6. So if this was just 3 alkenes, those H's should be 5 to 6. Why were they at 7 to 8 instead? Well, because it's aromatic. But what about being aromatic moves the signals more downfield? First off, if they are moved more downfield, that says, hey, these must be aromatic H's. Because alkene H's are 5 to 6 typically. What moves them more downfield? I think this was discussed in the NMR handout. Anisotropic effects. Okay. The electrons in the ring are induced to have a current by the big magnet. By the way, moving to the left, is that shielding or deshielding?
Deshielding.
That's more deshielded. This H is more deshielded. Why? Because the induced current in this ring, the big magnet induces a current in this ring for these electrons, and an induced current, as you learn in physics, always opposes the thing that induces it. Okay? And the opposing is basically a deshielding effect. No, is that right? No, if you oppose it, you're going to make it feel less. That sounds like a shielding effect. Yeah. If you oppose the magnet, you're going to feel less magnet. It'd be like feeling less sun. That'd be like putting sunscreen on, and that'd be a shielding effect. Okay? So that doesn't make sense. Why didn't anybody call me on that? So why is it apparently being deshielded? Anybody have any more handout? Good.
It's actually reinforcing the external field. The
Yes,
external-
because this is why it's called an anisotropic effect. Anisotropic implies direction. Okay? Direction of the induced. Here's the external big magnet with this direction. It induces electrons here to have a direction. And say it opposes it. It must be more complicated than that. My physics knowledge is kind of handy, okay? So you're going to have to. But this has directionality. And it sort of circulates here. But out here where this H is, the direction is known to be pointing up, in line with this. So it's adding to the external field. Okay? Now, if you're in the sun and you put on sunscreen, you're reducing the amount of sun you get. What if you put something on that increased the amount of sun you got? You get more sun. That would be you would not be shielding yourself from the sun. What's the opposite of shielding? De-shielding. Adding to this is essentially a de-shielding effect. And that's going to move your signal which way? Downfield. Okay? You have more of this with the aromatic system than you do with the alkene. All right? But in the end, we can look at NMR and say, are these aromatic H's or are these alkene H's? Okay? And all those four ways together, we can say, we really have a special compound, and it's not just three alkenes. We described all this as aromatic. Okay, guys. See some of you in lab tomorrow at 2:30 downstairs. We will do a little NMR review. Please be ready for that. And look for